you so much, Juan, and for that presentation and review of my CV. And above all, thank you so much for inviting me here. I mean, it's a great seminar. It's a pleasure and honor to be with you. So yeah, today it's a talk based on one or two, depending on how time goes, joint works with Philippe Soufflet from Sorbonne University in Paris. And well, it's gonna be on two problems. Most part of it's gonna be on two problems in the qualitative theory of elliptic PD, namely the validity of the strong maximum principle and the so-called Landis conjecture. And it would mostly be about the sort of a new method of proof that we devised with Philippe, which is based on the weak Harnack inequality with optimized constants in terms of the domain and the coefficients of the operator that's involved. So let me start this talk. To start with, the setting is we are given a uniformly elliptic second order operator, which might be either in the general divergence form or in a general non-divergence form. Both are going to be considered actually jointly here. I mean, one can even have more generally a fully nonlinear, say, Hamilton-Jacobi-Bellman or Isaacs operator, for instance, a Pucci type extremo operator. But to keep the presentation as clear as possible, I'm going to stick to linear operators, right? That are indeed here in the general form. And so LD and LND will refer to the type of operator, and essentially they will be considered jointly. So I'll just say L of U and mean in any of these. And in general, we'll be considering weak solutions of equations involving such operators. Weak in the usual sense that is in the divergence form of weak Sobolev solutions and viscosity solutions for operators in non-divergence form. Okay, so let's remember that A stands for second order coefficients, B stands for first order coefficients, and C stands for zero order coefficient. Yeah, and we'll make assumptions that essentially guarantee that such operators can verify the general maximum principle and the Harnack inequality, generalized maximum principle of Stampakia type for divergence for operators, or Alexandrov-Backelman type for the non-divergence type operators, which means, okay, so we are having uniformly elliptic operator with bounded coefficients, and we assume that the first order coefficients are some LQ spaces for, say, some Q bigger than N, and the zero order coefficients is in LP for some P, which guarantees these properties, which is N over 2 for the divergence case, and a constant which is unknown, but between N over 2 and N for the divergence case. Right, so that's essentially, I mean, not the weakest possible, but say the weakest possible in terms of Lebesgue spaces coefficient hypothesis that guarantee these basic properties here.
Sorry, what is M plus minus in the definition of the operator? Before this, yes.
Yeah, the Pucci extremum operator, the maximum of or minimum of all such operators with A between small lambda and big lambda.
Thank you.
And yeah. Okay, so let me recall the very, very well known standard result, right? The so-called strong maximum principle. One of its forms is the following: given a non-negative super solution of an equation like that, which vanishes at one point, then it vanishes everywhere. Yeah, and of course, in the linear case, this is equivalent to saying that whenever subsolution touches a super solution from below, they need to coincide. This is a very fundamental property in the theory of elliptic PDEs. Right, and in that form, it was observed already in 1984 that this is not actually a linear result, right? That it is possible, Vasquez in 1984 proved that, for instance, it is possible that the zero order dependence here may be non-Lipschitz at zero in U, right? So it is possible to find functions f of U that are not linear like when U is small, but still this property is valid for the equation of Poisson of u minus f of u. I mean, for the operator 1 of u minus f of u. Yeah, and now of course recall this result in the following. But so that result. Let me introduce it by very quickly reviewing these properties, the strong maximum principle. Of course, to start with, if you have a concave function which attains a minimum, then it is a constant. Okay, elliptic PD theory tells you that you don't have to be concave everywhere. It's enough that you have more concavity than convexity, that the trace of the second derivative be negative, and you still keep this property, right? So more concavity than convexity still tells you that when you attain a zero minimum, you have to be constant. And then adding terms, they say adding terms of zero order. It's you can see it like that. Okay, given a positive function which attains a zero minimum at some point, you cannot put under it its Laplacian. I mean, there's no function which is positive and has a zero minimum somewhere, such that its Laplacian can be put below it. So this is like you can see it in this way.
Sorry, d square and delta are different operators. D square and delta.
D square is the Hessian. It's as a matrix.
Ah, thank you.
Yeah, so this is like saying the function is concave. And the Laplacian is the trace of the D square. And on the other hand, if you may wonder, okay, can I put something bigger than u here, a function of u which is bigger than u? And this property might still be true. And to start with, of course, you may look at powers. And already any power smaller than 1 here breaks the result. I mean, it is easy to find functions, which actually C2 functions just powers of the radius. C2 functions such that they vanish at a point, say at the origin, and they're positive, and they are not identically zero, and they satisfy such an inequality. So, I mean, u is okay, u to the p with p smaller than 1 is not okay, it's too big. They are functions such that their Laplacian goes below u to the p. And what Vasquez proved in 1984 is that actually there is an exact threshold between u and u to the p, and it is strictly between u and u to the p for p smaller than 1. More specifically, the result goes as follows. Let's say we have a function f, which is 0 at 0, be non-decreasing. And it is such that its primitive, a primitive of f, is non-summable. The square root of the primitive is non-summable at 0. Then the property keeps true. The strong maximum principle is still true. That is, this holds. I mean, if you have a positive super solution which vanishes at one point, it vanishes everywhere, right? Classical super solution. So of course, if f of u is u, this is square root of the primitive is again s, and this is just the log of s here. But there are functions which are non-Lipschitz at 0 and which satisfy this. The most standard basic examples are functions f of u that grow like s log s to a power which can be smaller or equal than 2 at 0, right? This is the most, actually the only examples for which I've seen this to be applied somewhere, right? Which some applications. So this is the main example of a non-Lipschitz function, non-linear function for which it is the Vasquez conditions. And I'm going to refer to this condition over here as the Vasquez integral condition. For which this the strong maximum principle still is true. Right, just a remark that maybe you've seen this such a condition also. This condition is similar to what one sees in the so-called Keller-Rosserman condition for existence of entire solutions of such equations. But then the integral is at infinity. So they are not exactly directly related, even though they have something in common. These conditions. Okay, so. Now, after Vasquez works and up to today, there's been really a lot of work on extending the Vasquez maximum principle to weak solutions and to more general operators, if quasi-linear, fully nonlinear, singular, degenerate based on the like modeled on the pure Poisson, and so on. Actually, there even is one quite well-known book essentially devoted to this problem, the maximum principle, by Patricia Pucci and James Herring. In that paper, they proved the Vasquez maximum principle for very general divergence form operators. I mean, they show also that the integral condition of Vasquez is necessary for this result, that it is sufficient that the function, the nonlinearity be non-decreasing only in the neighborhood of 0. And recently, people realized that in some particular cases, this condition, the latter can be even be removed. But also there's been a couple of works for the non-divergence form operators, fully nonlinear type. But what previous results shared is that they all assume that the operators in consideration have all their coefficients bounded. And that is due to the method of proof. And the method of proof of that's essentially almost always being used is the usual proof, if I may say so, of the strong maximum principle. And I'm going to recall that proof now. And we see how the Vasquez integral condition comes in. So how do we prove? I mean, this is the standard way of proving even in the introduction PDE class of proving the maximum principle. The strong maximum principle goes like this. First, you prove say comparison principle for your operator. We say good coercivity, right? Say we prove that else we say the good sign of the zero order term is satisfying the comparison principle. So that's the maximum principle. Once you have the comparison principle, you look for a radial subsolution of your equation in any given annulus with different values on the two boundaries of the annulus. And this you want this subsolution to have a non-vanishing normal derivative on the boundary of the annulus. Once you have such a subsolution, using comparison, you can deduce the Hopf-lemma for supersolutions of L of u smaller than 0, right? This counts by comparison with this radial subsolution. And once you have the Hopf-lemma, there is an analysis argument, continuity connectedness argument, which deduces the strong maximum principle. This is like the most standard proof of the strong maximum principle. And now, when you apply these two equations that are nonlinear, like proportion of u plus f of u, you see that actually the Vasquez integral condition will appear in the step 2. I mean, when you try to construct the radial subsolution, you essentially try to solve an ODE, right? And to get this ODE, you need a radial equation. For instance, if your initial equation is this one, say with some b of x, you look for a radial solution with replacing b, but by its minimum, right? And in some annulus, this gives you an ODE. And where does the Vasquez integral condition comes in? It tells you that the derivative of the initial value problem for the ODE corresponding to radial solutions of this would not vanish precisely if f satisfies the Vasquez integral condition, right? Once you write the ODE, say the solution of the ODE corresponding to this with value 0 and 1, say at 0 and 1, you see that the derivative of 0 of that function is not 0 precisely if f satisfies the Vasquez integral condition. It's actually an ODE result, right? And to do this, you need B to be bounded here, right? So to date, there were no results. This was open, actually, whether it's possible to prove the strong maximum principle for operators that have unbounded coefficients. And observe that actually for operators with unbounded coefficient, the strong maximum principle has been known for a long time but through a different proof using the Harnack inequality or the weak Harnack inequality of Moser, to start with, the Georgian Moser, which indeed that proof works for, and I'm going to come back to that. That proof works for operators with unbounded coefficients. But when you take nonlinear operators, there's no extension of the Georgian-Moser Kirov-Stefanov results. And the only proofs of the Vasquez type strong maximum principle with non-Lipschitz nonlinearity required bounded coefficients. And that's what we proved in a recent paper with Philippe, is that actually it is possible through a different proof than this one that I just presented, that was used for Vasquez type strong maximum principle, to prove that indeed the result holds, provided the nonlinearity has that growth of my main example here, right? Of my main example. If we have such a growth at 0 of the nonlinearity, right? If f does not explode, if the derivative of f is no worse than 1 over log of s at 0, then the result holds. I mean, I've put here essentially infimum of u in case u is not continuous, but if u is 1 point, it vanishes at 1 point, then u is the trivial function, right? So essentially for all, for the main example and for all this, which is actually the only thing that we encounter in applications too, we do have the result for operators that have unbounded coefficients, right? That's the result. Okay, just I'll just spend one slide here to tell you how I realized that such a result, that this was open and necessary to prove for some other completely different, in a different situation. I mean, studying problems of so-called natural growth, I mean, boundary value problems for operators with so-called natural or quadratic growth in the gradient. So take the operator L, which I have divided here between 0 order term and high order terms, and add a quadratic term in the gradient, some bounded metric same, say. So such problems have been studied very strong, very much in the past, in particular in the coercive case when C has a negative sign. And in the last 10 years, probably, there appeared a number of works for the much more complex non-coercive case when C may be positive or change sign. And proving existence results for such equations often requires topological methods and proving first a priori bounds in L infinity for such problems. And recently, with my former student Gabriele Norberg, actually she was mentioned, she went to Chile recently, we studied such problem for non-divergence problems, non-divergence type operators, and we realized that the crucial a priori bound hinges on the strong maximum principle for a modified operator, actually and which involves precisely a nonlinear term of the form u log u. And so the strong maximum principle for such equations was available only for bounded coefficients, and in that work we had to restrict everything to bounded coefficients because we did not know how to prove the strong maximum principle for this inequality. Now, with this extension, for instance, all these results about the existence of solutions for such inequalities with fully nonlinear operators, say, are extended to the natural setting of operators with only integrable coefficients. Just one application, actually, of this result. Okay, so let me move now to go back to the result itself and make a few comment on a few things here. So here's once more the theorem. So if we have a nonlinearity whose derivative is no worse than log s to the square, then the strong maximum principle is true. So the method of proof absolutely does not see any monotonicity assumption on F because it's not based on comparison. So that's removed too. That's one observation. And first open problem, of course, here is, does actually the result hold under the integral hypothesis on the function f? See, this is stronger hypothesis, right? I mean, we can prove it under this, but we cannot prove it for f, which is like s log s to the square log s. We do not know if it's true or not. I mean, if you add a log, the integral condition is true, but this is not true, and our proof does not apply. Well, the integral hypothesis is quite an ODE hypothesis, right? And since we do not know an ODE method for proving this result with unbounded coefficients, it's really not clear. Well, that's one observation. So what's the method of proof? The method of proof is to use the weak Karnac inequality, in which we optimize the constant with respect to the size of the domain and the norms of the lower order coefficients of the operator, right? So that's the general idea. So let me recall these things a little bit, of course, because I don't expect the audience to be expert on that on this. So what's the weak Karnac inequality? Here's the most usual form of it. It tells you that if you have a positive super solution of the operator L in some domain, say a ball of radius r plus 1, then in a compact subdomain, say in a ball of radius r, you can bound from below U by some L epsilon norm of the U itself. And here this epsilon depends on the dimension and the ellipticity. And actually for the divergence form operators, it depends only on the dimension. Actually, you can go up to n over n minus 2. And this constant here is something that depends on the ellipticity, on the P and Q. Let's recall P and Q are the Lebesgue exponents for the respectively zero order and first order coefficients, right? And of course, of these norms, right? The first order coefficient, the zero order coefficient, and the size of the domain R. And what we are going to do is going to write this inequality with an optimized constant with respect to these quantities over here. And this somehow we imply the strong maximum principle. That's what's going to happen. So this is really a fundamental result in the theory of elliptic PDEs. For the divergence form operators, goes back to De Giorgi, was proved in extended forms in this form here by Moser and later Trudinger. For non-divergence form operators, this is a fundamental contribution of Krylov and Safonov by the late 70s and early 80s. And then extensions are due to Caffarelli, Cabré, and Koike-Swish for more general operators. So this is a quantification of the strong maximum principle, or in other words, it can be seen as a growth lemma. Why? Because it tells you that if you know that this positive or zero function is strictly positive on some subdomain of the ball, which you don't know where it is, but you know that it has just a positive measure, then you know that U is actually strictly positive everywhere limited by a constant which depends only on the measure of the set where U is strictly positive, and of course on the lower bound of U on that set. So it's a growth lemma, and one of its applications, probably the most known application, is the C alpha bound, the Helder bound on solutions of equations LU equal to 0. And there's also a non-homogeneous version of this result, which tells you that if you have a right-hand side, then this inequality is to be corrected with an LP norm of that right-hand side. That's it's a non-homogeneous version of this inequality. And yeah, so it's in that inequality that we're going to do some optimization of the constant C, weak Karnac. And also a little optimization is necessary also here, because see, the usual form of this inequality is like that. And it's not exactly very optimal with respect to the size here, because imagine if f is a bounded function, then the L infinity norm does not depend on the size of the domain. On the other hand, if you have a function which is just LP, say f is a constant, its LP norm would increase when r increasing. Say for f equal to 1, the L infinity norm does not increase when r increases, but the LP norms do increase. So some local norm is necessary here. And so we replace this norm here by local norms using so-called uniformly local Lebesgue spaces. These are very usual in parabolic theory. Go back to 14 Ibrevelo. So just take the uniform LS norm of a function to be the supremum of its LS norm over any ball with size 1. All right. And then let's define these things over here. So we're going to write M to be 1 plus the norm of our first order coefficient in the LQ uniformly local to some power, which is given here, where 1 over 1 minus n over q, this is homogeneity powers, and also plus the 0 order coefficient in LP to some power, which is given over here, with r equal to p. In particular, let's observe that if p and q are infinity, then this power here is 1, and this power here is 1/2, right? If p is infinity, gamma infinity is 1/2. So it's like 1 plus b plus square root of c. Let's think of it. There's 1 plus b plus square root of c to make it simpler. And then it is possible to prove that the constant in the Wick-Harnack inequality is always smaller than a constant time exponential of this times the size r. Right? It is obviously optimal in the sense it cannot be better than that. You see that even from ODE. I just write an ODE, and you see that solutions are essentially like b plus square root of c, right? So I mean, it clearly cannot be better than that. But what we see is that here, what you see is it is exactly like that. That constant can be bounded by an exponential of this quantity times the radius. Okay. So once we have this, yeah, let me. I'm not going to give proofs, but I'm going to explain because it's not difficult to understand why things work. How do we prove that? Well, with this quantity here, if we take a ball of size 1 over that and rescale it to a ball of size 1, the new rescaled operator will have coefficients with norms which are smaller than 1. So essentially, to width, you can apply the usual Harnack inequalities for coefficients that have norms 1 in a ball of size 1. And so you get a uniform constant for the rescale operator. Then you scale back, do a covering with overlapping balls with a Harnack chain argument, which you optimize with respect to the geometry, and we end up with this constant here after some technical work. Also, it is possible to optimize in a similar way, and actually in quite simple way, the so-called local maximum principle, which is a result for subsolutions when you bound the maximum with respect to some L epsilon norm. And then we see that an optimized constant here is even polynomial in that quantity m, and not exponential. When you put these two together, you get the full Harnack inequality. If you have a equality in the equation, you get supremum of u smaller than infimum of u times exponential of this quantity. Okay. Once we have that, here's an idea how follows the Vasquez strong maximum principle under our hypothesis. Again, just an idea. So linearize the equation. Think that we have our equation, linearize it, and see this log of u to some power as a 0 order coefficient, and apply this weak Harnack inequality. Okay, you cannot immediately apply it because u is 0 somewhere. This is a function that you don't know if it is integrable, and it usually will not be. But imagine we could do that. Of course, this is not true just like that, very formally. Imagine you could do that, and then you would have this c would be this walk to a power 1/2. And then write this inequality. So what's happening here? This infimum is 0, And this M here is infinity, right? Because we are taking this thing here is infinity around the point of minimum, log of 0. So in this inequality, we have an indetermination of the sort infinity times 0. Okay, after some technical work, you prove that actually, if this A is more than 2, you resolve the indetermination in favor of the 0. So actually, this infinity times 0 is 0, and so this integral of u is 0, and so u is 0. So this is the idea of the proof. Okay. One more open problem about the Wicker-Nack inequality. So we prove the strong maximum principle for the nonlinear operator, but using a linear result, right? We use the Wicker-Nack inequality for the linear equation with an optimized constant. One may wonder, wouldn't there be a Harnack inequality for the nonlinear equality itself, or at least for solution of an equality? And the answer of this is yes. This is a hard paper in a very particular case by Vasquez from a couple of years ago. If you just have solution of a pure divergence form operator, no first order terms, no zero order terms, and solutions, then you manage to prove something very exact, that actually you can bound by a uniform constant the integral from infimum of u to super v of d of s square root of the primitive. Of course, if f is linear, this is just the usual Harnack inequality. And this uses the divergence structure. It uses so-called de Benedetto-Trödinger approach, where you write an ODE for the volumes of super-level sets of the solutions. It's a hard result. An open problem is if such a result would be true for more general second-order operators, or for nonlinear second-order operators, or just for a Pucci operator. Would such a result be true maybe by some more fine iteration of Landis Krylov form of the Ferrari type? This is another open problem. Okay, now I move to the second problem we studied through an optimized Harnack inequality. It's at the first glance a very different question. It's actually a very different question. An open problem, which to my knowledge appears by in a famous survey by Kondratiev in Landis, but it appears to go back at least 20 years before, in the 60s, is the following. It's a very, very simple thing. Take the Schrödinger operator, Laplacian plus a zero order coefficient, and assume we have an even bounded second zero order coefficient, and assume you have a solution of this in some exterior domain. Is it true that such solution cannot decay super exponentially at infinity? Very simple, all right? Or more precisely, is it true that one can find a constant which would depend only on the infinity bound of this C, such that if this limit is 0, then u has to be 0, right? So if u decreases very quickly, more quickly than exponential minus mx, then u has to be the trivial function, right? Okay, in spite of the apparent simplicity, this is still open nowadays. We do not know the answer of that. And let me review very quickly the history of that conjecture. So it was stated first to start with for complex solutions and complex potentials. And yeah, there are also different versions of the same conjecture. First, variants of that conjecture, yeah. First, what if the problem is not given in an exterior domain, but in the whole Rn? Even that is still open. There's a weaker conjecture due to Koenig from about 15 years ago. Is it true at least that solutions cannot decay quicker than exponential of x to a power bigger than 1? For at least for n bigger than 2, this is also still open. And of course, can we consider more general operators than Laplacian here? All right, so there are some variants of this conjecture that we consider true. Well, first, a few years after this question appeared, it was disproved for complex equation. Interestingly, if C is a complex function, then the result is false. And actually, there are even complex solutions that decay yx to the 4/3, and it's optimal. In that line, there's been a lot of developments. This is not what I'm considering here. And these are related to Karleman type estimates that do not distinguish between real and complex solution. So the conjecture, which is still open in the real case, well, it cannot be achieved by such techniques. But interestingly, this, at least in the complex case, it's false, and actually 4/3 is the right rate of decay. Well, now for real equations, in the last couple of years, there appeared few results in a paper that became well known by Carlos Koenig with Silvestri and Wang in 2015. They considered this problem in R2 in the divergence case with some additional hypotheses, and they prove a quantitative bound, which says that within distance of each point on any sphere with size r, there's a point at which you use at least exponential of r log r. So at least it proves Koenig's conjecture, which tells you that it cannot be r to the power 1 plus epsilon. And also for exterior domains, then there's r log r square. There's a number of generalizations of this paper, all for dimension 2 and equations in divergence form, with various hypotheses on the war of the coefficients, which in particular imply, that's a basic hypothesis in these sides of problems, is that the operator satisfies the maximum principle on bounded subdomains of Rn, say if the problem is put in Rn, R2 in this case. Essentially, this means that the generalized first eigenvalue of the operator is positive for 0 in Rn. Okay, then Luca Rossi, 2 years ago, proved that a similar result for non-divergence form operators, now again assuming that the operator satisfies the maximum principle on bounded subdomains. And through a comparison result, using the fact that if the operator has bounded coefficients, then you can find the subsolution, which is exponential to minus mx, if m is big enough. So there's a comparison argument to be done there. And it works in every dimension, provided, again, the operator satisfies the maximum principle on any bounded subdomain. There are also related results to this one by probability techniques and by a duality method that I'll come back probably later. Right. So this works in any dimension, right? For operators that are in non-divergence form instead of divergence form. 2 years ago appeared a preprint, which is the only paper that I know of which does not make this hypothesis on the coefficients of L that makes it satisfy the maximum principle, or that makes it to have a non-zero, to have a non-negative first eigenvalue in Rn by Logunov, Malinnikov, Nadir Shleri, and Nazarov, which says in particular that the Koenig's form, the weaker form of exponential 1 plus epsilon, is valid in 2 dimensions. And actually, they prove more precisely that decay of any solution of this problem can be no worse than exponential minus x square root of log x. This is really a 2 dimensions result because it uses quasi-conformal mappings. Higher dimensions is still open. Without that condition here, maximum principle on bounded subdomains. That's the only result that I know of which avoids it. And it's a hard result, and it's a 2-dimensional result. For unbounded coefficient, there's been a couple of works on a little bit with a little bit different hypothesis, assuming that the coefficients are integrable at infinity, which is a strong hypothesis because this means like decay of conditions at infinity. then actually one can prove that you cannot grow even less. I mean, it cannot grow like even like exponential of x to the alpha with a alpha which is more than 1. It's a stronger result, but you pay very much in terms of restrictions on the coefficients. You ask them to be integrable at infinity, that is to have decay. Yeah. So here it's you get. So our contribution here is to prove the Landis conjecture in any dimension for any unbounded order coefficients that allow the Harnack inequality to hold, which are only uniformly locally integrable. So bounded coefficients are a very particular case, but under this hypothesis that the maximum principle holds. I mean, this hypothesis we cannot avoid. That's and here's the theorem. Here's the theorem, exact theorem. So the result is the Landis conjecture is this thing here. And yeah, we prove that if we have Rn or an exterior domain and an operator, which can be either in divergence or non-divergence form, then we can prove that there is a constant which depends only on the ellipticity and dimension and exponents in Lebesgue spaces, such that if we have a solution which grows more quickly, which decays more quickly, exponentially and more quickly than exponential C1x, where C1 is this C0 times exactly this quantity here, then U has to vanish. It settles exactly the Landis conjecture under this hypothesis on the maximum principle being valid. So for coefficients which are not bounded. So a quick idea of the proof, again, this theorem, the theorem is again here, and a very quick idea of the proof is we can construct a signed solution, a solution that has a sign of the operator in the domain, let's say in Rn. Okay, but then once you have a signed solution, you have that sharp Harnack inequality with optimized constants. And it tells you that this condition, this solution, this signed solution would decay at most exponentially. So if you decay quicker, we can use the maximum principle, the comparison principle, to squash U with the psi, right? We can squash it by simply comparing U with any positive constant times psi on intersection of omega with a large ball, and prove that plus minus U will be smaller than delta psi for every delta positive. So U has to be the zero function. So this is essentially the idea. Of course, there's some technicalities to do. And so to conclude what I've been saying up to now, this is a new approach which unifies the treatment of these two classical problems that never have been considered, of course, jointly. And it has the following main advantages. So it gives answers for operators with unbounded order coefficients in a number of situations where all previous results required bounded ingredients. It extends the Landis conjecture to operators with bounded coefficients in situations where it had never been considered, for instance, in fully nonlinear equations. This was completely open. And it has the advantage that it treats simultaneously equations in divergence and non-divergence form, because it's based only on the Harnack inequality, and the Harnack inequality is valid for both types of equations. And essentially, and the proofs actually, once we have that Harnack inequality, which is optimized, is quite short, in fact. And so the tools are the weak and full Harnack inequalities with optimal dependence of their constants in the order terms in the size of the domain. That is to conclude. And now, since I have a few minutes yet to my 50 minutes, so I'm gonna spend them to show a result, which is a few more recent results that's actually in preparation now with Philippe, for more precise forms of the Landis conjecture. So once more, the Landis conjecture tells you the following. If we have a solution of the equality like that, say in Rn, then for sufficiently large m, the lim sup of exponential mx ux has to be strictly positive. So now, first and easy observation is that this is not true if we replace the lim sup by lim inf. And even it is not true that, say, if we take U on any sphere, large sphere, you can bound the integral of U by some negative exponential. Even that is not true. And it's easy to give counterexamples. Say this function which solves this inequality, this equation in R. And of course, it vanishes. The module of U vanishes over a sequence which goes to infinity, wherever the cosine is 0. So that's this more precise form of what is conjecture cannot be true in general. But interestingly, okay, let's note that this operator, this counterexample here, does not satisfy that hypothesis on the maximum principle on bounded subdomains. I mean, its first eigenvalue in R is -2, right? So one may wonder, and what if the maximum principle held? Could we prove this stronger form of the Landis conjecture? And that's what we prove with Philip recently in the divergence case for divergence form operators, and under the extra hypothesis that they have C1 estimates. This we do not know how to remove. This means that we have to reinforce the hypothesis on the coefficients of the operator, like assume, for instance, Hölder, that the leading coefficients are Hölder, that the lower order are O L cube for Q bigger than N. Say C estimates are valid. And then we can prove that indeed, if we have a solution like that, say in Rn, then the integral of U over each sphere is bounded below by a constant, depending on U, of course, times exponential of -mr, where m is again something which measures exactly the coefficients of the operator. And the constant, we can see that it's even, we can take the integral of U over the whole ball. Right? So it's quite a more precise result. And we can prove that this type of result, on the other hand, is indeed, for that, it is necessary to have the maximum principle in each bounded subdomain. I mean, that hypothesis, which is probably superfluous for the Landis conjecture in this form, is not superfluous for this more general hypothesis, for this more precise inequality here. Yeah, so that inequality cannot be true for operators that do not satisfy the maximum principle. Actually, we prove that for every lambda, we can find an operator so that has a first eigenvalue, which is minus lambda, and this fails. We can find a function which solves it and vanishing on a sequence of spheres, and for which the lim sup is 1. Yeah, so this stronger form indeed requires operators which satisfy the maximum principle in bounded subdomains. Well, again, a very quick idea of the proof of that, and I'm going to finish with this. Now, we need to optimize the constants in two more results from, say, basic elliptic theory. First is the say the boundary Harnack inequality, and that's where the C1 estimates are necessary. The boundary Harnack with optimized constant, it has a very similar form to the Harnack, but it goes up to the boundary. If we have a positive function which satisfies an equality and vanishes at the boundary, then one can bound the U over the distance to the boundary with U over to the distance to the boundary and the optimized constant, which has the same, which is of the same type. And from that, we are able to infer optimized Stampacchia maximum principle, which says that if we have a divergence form operator and a solution of the Dirichlet problem for that operator, then that function is bounded by a constant times LQ norm of the right-hand side. This is the Stampacchia result, but the optimized constant is again the same exponential. Well, once you have this, essentially, you can take your equality, you can start using things like solve this for f being the sine of u, multiply, integrate, and you get a result over for the integral of u on spheres by the divergence theorem. And actually, you check that in the end, you end up with things like this after some technical work. So that's and we also have various other optimized results in terms of coefficients, such as quantitative Hopf-Lemma, C1 estimate, Wograd estimate. But I'm gonna stop here, and we'll thank you for being here. Once more, thank you for inviting me.